All right, AP Chemistry. We're continuing the Day 81 assignment with problem 14.55 from your textbook. That's on page 620. So the problem reads, a certain first order reaction has a rate of 2.75 times 10 to the minus second, seconds to the minus 1. So K is that number at 20 degrees centigrade. What is the value of K at 60 degrees centigrade? And then they give you two different situations with two different activation energies. Okay, so the best way to always approach a problem like this is to go ahead and write down the variables that you have and what you're looking for. And a lot of times when you do that, the formula that you need will kind of jump out at you. So we'll go ahead and do that. All right, so the problem gives us a value of K at a certain temperature, and it's asking us for the value of K at a different temperature. So let's go ahead and write that down. So we have K1, we'll call it. And that's the value they give us. And the units is 1 over seconds, or seconds to the minus 1. And that's at T1, which is 20 degrees centigrade. Now we're going to convert that immediately into Kelvin. Or anytime it's not well, anyway, go ahead and convert that to Kelvin. Always play it safe and convert everything into Kelvin. Sometimes you need to, sometimes you don't. It's really just kind of experience when you do and don't need to. In this case, we're going to add 273 to that. And that gives us 293 Kelvin. Okay, K2. And I'm going to write that up at the top. K2 is question mark. That's what we're looking for. We're looking for a second value of K at temperature 2. And they say that's 60 degrees centigrade. And we convert that to Kelvin. All right, and then in situation A, so these data are going to apply, and questions are going to apply to both situations. In situation A, they're telling us that the activation energy is 75.5 kilojoules per mole. Okay, all right. So you look at K, you have two different values of K and two different values of T. And if you go back to the formulas that we had in the video and in the notes, or if you went back in your book, you find the following formula. Okay, so this formula gives us two values of K, or requires two values of K, two values of T, and an activation energy and a gas constant R. You have to be sure which gas constant you need to use. How do you do that? How do you know which one? There's several different versions of the gas constant R. Again, it's just by practicing doing problems. It's not by trying to memorize it. And so for this particular type of problem, pretty much any problem we do in kinetics, we do the value. I'm going to go ahead and write it up here because this will apply to all of the problems. It's R equals 8.31, and it's joules per mole Kelvin. So we don't use the 0.0821, the one that we've used it for the ideal gas law, PV equals nRT. It's the same thing, it's just in a different unit of measure. It uses joules in the numerator here. Okay, so what we see is the following. We have this number, we have two temperatures to work with, and we have K1. And so what we're trying to find is K2. All right, so let's go ahead and do that. One thing we're going to need to do, though, is the activation energy is in kilojoules per mole, and the gas constant is in joules. So we're going to need to convert kilojoules to joules. That's one of the things the gas constant does for you, is it tells you what units you need to work in. That's why we knew that we had to convert from centigrade to Kelvin, because it has Kelvin in it. So always look to constants in general, but in this case the gas constant R, to tell you what the units of measure are that you're going to have to deal with. Okay, so let's go ahead and do this. So I'm going ahead and doing my kilojoules to joules conversion right here in the problem. Okay, I'm going to pause, and I'm off screen a little there. I'm going to pause and go ahead, and I'm going to double check my numbers. You go ahead and double check your numbers. All right, so I've checked the numbers. Now, one of the most challenging things in working these kinetics problems is just the arithmetic, the basic math and algebra can be tricky because some of the equations are kind of big. So what we're going to do is we're going to start off by simplifying this side of the equation. And I'm going to start off by simplifying this. So if you take, and calculators use order of operations. That means it does multiplications and divisions before it does additions and subtractions. So if I simply typed in 1 divided by 333 minus 1 divided by 293, it will execute that properly, because it'll do those two divisions, this one and this one, before it does the subtraction, and that's what you want it to do. If you're not sure, though, it's a good idea to put a parenthesis around 1 over 333, 1 divided by 333, close the parenthesis, then put a minus sign, and then put another begin parenthesis, 1 divided by 293, and then close that parenthesis. So we're going to go ahead and do this. Once we've done that and have that number in our calculator, we can multiply it by 1,000 and by 75.5. Or if you can do this in your head and you know that it's 75,500, this right here, you could just go ahead and push that in. And then you're going to divide by 8.31. Now let's check to see how our units of measure, whether they cancel properly. So up here we have kilojoules and kilojoules. Here we have moles and moles. And again, you may need some practice doing a fraction in the numerator and another fraction in the denominator. So you have two fractions within this major fraction here. You got to be sure you know how to handle that properly. We can come in and practice with me, or we will practice between now and the AP exam. All right, now we have joules in the numerator up here and joules in the numerator here, so they cancel. So the only thing we're left with here is K Kelvin. And since it's in the denominator of this bottom fraction here, it flips. It's just like flip and multiply when you do a dividing fractions. It flips and comes up to the top, so it ends up here. It ends up on the top up here. Then you have K's on the bottom there, so the units are all going to cancel out. All right. Okay, so here's what we're going to do. We're going to do, and this is, I'm going to tell you exactly how I'm going to punch in these keystrokes. I am going to start over here, and I'm going to say 1 divided by 333 minus 1 divided by 293. So that takes care of this. Now I'm going to multiply by the top up here. I'm going to actually hit an equal sign, and I end up with a negative 0.000409966. Anyway, as long as you have all those digits, you can just leave them on your calculator. You don't have to clear them. But I'm going to go ahead and write it down here anyway. 0.0004, and 0.99 is just going to round right up to 41, and that leaves me 5 places after the decimal. It's only 2 significant figures, but it's 5 places after the decimal, so I'm going to leave that there. Now I'm going to take what I have on my calculator, which is not exactly this, it's a few more digits, and I'm going to multiply it by 75, multiply it by 1,000, then divide by 8.31. Times 75.5 times 1,000 divided by 8.31, and it's technically 314, so I'm going to go ahead and use all those digits. And what I get for this entire term over here on the right side, I didn't figure out what just that is by itself, but what I end up with the entire thing here is negative 3.7229. Okay, so over here on this side I have equals natural log of this. Now, the natural log of a number divided by another number, we talked about this principle, is equal to the natural log of the top number. And since this is only 10 to the minus 2, I'm going to convert that to just a regular decimal number. So I'm going to move the decimal place over 2 places. So hopefully this isn't a trick to you. If you want, you can keep it in scientific notation. But I'm going to convert it to 0.275. That's what this number up here equals that in decimal. You just slide the decimal over 2 places to the left because of the negative 2, and that gets you there. Okay, and let me erase this. Okay, and then that's going to be minus natural log of k, and this is k2, of k2. And it's going to equal that. So remember that this natural log of this divided by this equals the natural log of this minus the natural log of this. That's one of the principles of logs we talked about earlier in this unit. Okay, so what do I do now? Well, now let's take the natural log of this, of 0.0275. And that's going to give us negative 3.59357. Yeah, I'm doing a lot of significant figures here because I don't want a lot of rounding error. Remember, even when you're doing significant figures, you don't round anything in the middle of the problem. Well, realistically, if we have 10 digits on the calculator, we have to round somewhat. But I usually go to, 5 or 6 digits before I cut it off. Okay, and that's going to be minus natural log of K2. Okay, so now what I'm going to do is I'm going to add this to both sides. Well, there's several ways you can do this. I'm going to actually add this to both sides. Okay, and we'll do that. And it gives us this. Equals what's left on the other side. This canceled out, so you have negative natural log of K2. And now you can just multiply through by -1. I think you can all see that to make these positive. So that becomes natural log of K2 equals the positive of this. So now, how do we get rid of the natural log? We raise both sides to the e power. Okay, so remember that principle. That's how you get yourself out of a natural log, is by raising both sides to the e power. So this e to the ln K2 is simply going to equal K2. It undoes it, it inverses it, gives you just K2. And now we go to the calculator over on this side and you push second ln. That gives you e caret parenthesis 0.12933, close the parenthesis, hit equal, and you get 1.14. Okay. And that is your answer. K2 is 1.14, and it's 1 over seconds is the unit of measure for K2. So that is the answer for part A. Okay, now we're going to go on to part B. This will give you a chance to practice one and see if you can do this, see how much of this you can do without looking at part A, but they're done exactly the same way. So the only difference in this one is they give you a different activation energy, EA. And that's 125 kilojoules per mole. I'd like you to get out of the habit of writing fractions like with a slash. Write them one number, even if you have to use 2 lines on your paper. It's okay, paper's not expensive. Just go ahead and write them like that, because when you need to cancel units, you want them to look like fractions, and you want them to be on different levels. So let's go ahead and do something we know we're going to have to do right away. We're going to multiply this by 1,000 joules per kilojoule. Cancel, cancel, and you end up with 125,000 joules. We saw in the last problem that we had to do that. So let's just go ahead and do it. So that's going to be joules per mole. That's our EA. Okay, we had the same other data. I'll go ahead and write it again. You don't have to. It's 20 degrees centigrade, so that was 293 Kelvin for T1. We had T2 they don't change those numbers, is 333 Kelvin. And we had K1 equals 275 times 10 to the negative second, 1 over seconds, or seconds to the minus 1. And I'm going to go ahead, since it's a small, relatively, it's not a huge number, it's to the negative 2. I'm going to go ahead and write it as a decimal number. So 0.0275. Okay, and then again we have our gas constant R, and I recommend you always write these things out. Write out formulas every time you do a problem, even though it's the same, essentially the same problem. That helps you to memorize the constants, the formulas, and I think that's always a good thing. So this is 8.314, and it's joules per mole Kelvin. Okay, then what is the formula? The formula is natural log of K1 over K2, close the parentheses, so it's these two divided by this, and then you take the natural log of that whole thing, or as we saw, this converts into natural log of K1 minus natural log of K2. That's just a principle of logs, and it's one that we reviewed. Okay, so it's going to be equals EA over R. Write the pure formula before you plug in the numbers. 1 over, and you just have to remember that it's 1, 2, and then over here the first T is 2 minus T1. The address of the house I grew up in was 1221, so that's my mnemonic for this. 1, 2, 2, 1. So you just remember it however you need to remember that order. Okay, so now we go ahead and plug in numbers. Everything's going to be the same except this. So let's go ahead and do that. Okay, so check to see that that's what you got. So we are going to say this divided by this minus this divided by this. Again, the calculator will do the divisions first, and then it will do the subtraction. So we can just punch it in straight in that order. So 1 divided by 333 minus 1 divided by 293. Hit the equal sign. You get the same thing you got before. 0.00041. Multiply by this and divide by that. Okay, and for this side over here, what I get is this, and I'm going to write it to a lot of significant figures here, because technically we're not supposed to round anything until the very end. So I usually go to 6 or 7, sometimes at least 5. Or digits after the decimal, not even necessarily significant figures. Okay, so I'm going to leave it there. That's pretty good. Okay, that equals this. Okay, so you have that. So let's go ahead and calculate this. And we did that once before and we got this. Okay, now we're going to add this number to both sides. And over here it just goes away. So we end up down here with negative ln of K2. Don't forget that negative sign is still there. And over here we end up with negative 2.5. So now we can just get rid of the negative signs on both sides. Just think of it as multiplying through by -1 or dividing by -1, both sides, however you want to think of that, and you just end up with positives on both sides. And now we do our inverse operation on the natural log. End up down here, e to the ln raised to the ln K2 just gives you K2. They inverse each other. And now we plug this one in the calculator. And this gives us 13.07. Okay, and K is in 1/seconds here. Okay, and that's your final answer. All right, so the next problem is 14.58. The temperature dependence of the rate constant for the reaction is tabulated as follows, and it gives you a list of temperatures and a list of rate constants. It doesn't matter the order of the rate, but you can tell by looking at the rate constants that that would be a second order reaction. But that's not important, so it's just K is all that matters. So what they want to know is down there at the bottom of the table, it says calculate the activation energy, and A is the frequency factor. And that's a kind of a variable that includes a variety of factors that you're not going to ever need to know how to figure out, but it has things like orientation of the molecules. Are they oriented in the right direction? How they figure out all that is not something you need to know. It's just a number that either you're going to calculate in this equation or that's going to be given to you, and you don't really have to understand what goes into making A. Okay, so let's go ahead and get started with this one. Okay, so I've copied the data over to a piece of graph paper, and we're going to use graph papers. We're going to need to do some graphing. One of the things you want to look at when you're trying to determine how do you approach this problem is what variables you're given. So, and what variables are being asked for. So we're given temperature and rate constant. We're looking for activation energy and frequency factor. So immediately that should bring to mind the formula, the Arrhenius equation, which is K equals A E raised to the minus EA over RT. Okay, so now what we want to look at then, and let's go ahead and write the linearized Arrhenius equation. So that is obtained by basically taking the natural log of everything you see here. I'm not going to do the math, I'm just going to write the equation, and what that will give you is this. And that gives you, again, the reason we use natural logs in kinetics is to get a straight line equation, to turn something that's going to be, that would be a curve into a straight line equation. Now, as a straight line equation, it has a form of y equals mx plus b. So what's the m here and what's the x? Well, the variable is going to be, you can rewrite it like this. The y, which is your dependent variable, is going to be natural log of k. The slope is going to be this, and I'm going to put it in parentheses to separate it out. It's going to be negative EA, because EA is going to be a fixed number here, and R is a constant. So that's the m. And then the x, that would be the variable, is going to be 1 over t. So of course you put these two together to get that. So there's your x variable, that's your independent variable. There's your y variable, that's the dependent variable. And then the b is natural log of a. So if we want to plot this, what are we plotting? Well, we're not plotting t and k, we're plotting this independent variable 1 over t, and this dependent variable, which is equivalent to our y, is natural log of k. So we're going to go back up to our table here, and we're going to just do on the calculator, figure out what 1 over t is. There's the t values. We're going to just figure out 1 over t. So go ahead and take a minute and do that. Okay, so I've gone ahead and I've plotted 1 over t. Just take the reciprocal of these numbers and plug these numbers, make them natural logs, and you come up with this. So what you're going to do is graph this against this. The independent variable, that would be your x-axis in graphing, is going to be the 1 over t. The dependent variable, that's the vertical, or the y-axis, is going to be this one. So what you want to do when you do a graph and you scale a graph is you want to look at what's your lowest number and your highest number. So the lowest number here is 0.00125. The highest number is 0.00166. So on the horizontal axis, that's what we're going to plot, a range between those two numbers. And on the vertical axis, you go from negative to positive. So your lowest number is negative 3.5. And then your positive number goes up to 3.1. So let's go ahead and draw a graph of that. And you want to scale it. You're not trying to save paper here, so you want to scale it so it's reasonably sized so you can see where everything is. So, since I have to go from negative 3.5 to positive 3.1, I'm going to start down here, and I'm going to call this point right here, I'm going to call this negative 4. And let's see, I'm going to 3, 2, 1, 0. I'm going to go down even a little bit lower. Go way down here. So I'm going to call this point negative 4, and every 2 squares I'm going to call 1. So I'm going to go up 1, 2, that gets me to negative 3, 1, 2, negative 2, and you don't have to scale it exactly the way I'm doing it. Go up 2 more, you get to negative 1, 2 more gets you to 0, 1, 2, 3, and 4 right there. Go ahead and draw a line through there. And now at 0, we're going to have our horizontal axis. And that has to go from 0.00125 to 0.00166. So this is 0.00120, and we're going to go 1, 2, 3, 4, and just pick some number that's reasonable. 0.0013 0. Okay, so this should be able to fit all the points on my graph. All right, so go ahead and plot these points. So if we try to get everything on screen here. All right, so let's look at our first point. We've got 0.00166 and negative 3.5, almost 3.6. So negative, so 0.1166 is going to be down here somewhere, and the negative 3.5 is going to be down here. So again, it's just kind of an approximation, but it's right about there. And anytime you put a point, you should put a circle around it. It's called a point protector, so that you don't draw a line through that point, and so you realize that is actually a data point and not just a mark on the paper. So just circle it. Okay, next one is 0.154, so that's somewhere between 0.0015 and 0.0016, and it's roughly halfway. And then that's going to match up with negative 1.5. So I'm just going to come right here and come down here to about 1.5 right there on this axis. And we're going to put a dot right about there. Next, 0.00143, so that's going to get us just past 0.0010, and that's going to get us right around in here, and that matches up with 0.2624. So we come down here, so 0.2, and that's actually positive. That's a positive number. So we're now up into the positive numbers. So we're going to come up here, and 0.26 is going to put us right about here. Now we go to 0.00133, so that's right about there. And we go up 1.79, about 1.8, just a little below 2. So it's going to be right around here. And finally we have 0.00125, so that's right in between, right there. And we got 3.1, so we're going to go up just a little bit above 3, and that's going to be right there. And you can see we have something pretty much approximating a straight line, which is what we want to do. We want to linearize the data. That's the whole purpose of using the natural logs. So this was the natural log form of the Arrhenius equation. And so we can therefore derive a slope for that. And what would that slope be? That slope is going to be this. It's going to be negative EA over R. Okay, so now how do we figure that out? Well, we can get out a ruler and measure, rise over run. But what we can just do is pick our two extreme points. So these two right here for the y-axis, because that's the up and down, that's the vertical axis, and these two right here for the x-axis. So if you remember from algebra, your formula for a slope is y2, if we're using xy coordinates, minus y1 over x2 minus x1. In this case, the y's are going to be our, let's go ahead and label our axes here, natural k on this axis, and on this axis over here is 1 over temperature. Okay, so let's go ahead and do that now. So the we're going to take this point minus this point, so it's 3.1355. That's our biggest value of ln k, minus negative, don't forget the minus negative, it's minus and then it's a negative number here, 3.5756. So that basically turns into a plus sign. And then down on the bottom you have this 0.00125 minus 0.00166. So this is going to be 3.1 plus 3.5 and all of that. That's going to give you about, 6.5, somewhere in there, 6.6. And then this minus this is going to give you a negative number. And it should be, because your slope is a negative slope. So go ahead and do the math on that. And your slope again is negative EA over R is going to equal whatever that turns out to be. So go ahead and run that on your calculator. Okay, so again, the slope we found out up here is this. And if we run these numbers, we get this and we get this. And there's a bunch of decimal places after the decimal. But since we already have 5 significant figures there, I'm going to leave it there. So it's negative 16,369. So we do know the value of R. So what we're going to do is say negative EA over, this is our gas constant, and it's the one we're using, is the 8.314 joules mole Kelvin. And then equals negative 16,369. And energy, by the way, is measured in joules. So we're going to end up with an answer in joules. That's why I'm not too worried about what the units of measure are here. So now what we're going to do is multiply both sides by this, top and bottom. And this cancels with that. And you end up with negative EA equals this. And you get rid of the negative signs. I think you can all just do that. Get rid of the negative signs first. And so you end up with EA is going to equal the positive of that number. And what that will give you is 136,000 joules, or you can call it 136 kilojoules. And it's per mole, by the way. Second part of the question, we can use the Arrhenius equation. Go ahead and write it out in its pure form. And we did that on the previous page. Okay, so this is an exponent of E here. So we're looking for A. We know values of K. We have them in the table. We know EA, we just figured it out, and that stays the same for the entire problem because it is the slope of this line, of this straight line, and that has the same slope all the way up and down. So anywhere we are on this line, it's going to have the same number, which is the 136,000 kilojoules, or 136 kilojoules, or 136,000 joules. So that's what EA is going to equal. R is 8.314, and temperature is what we have on our table. So we're going to go ahead and plug in the numbers. We pick any combination here of temperature and K. So let's just go ahead, and I kind of like this one because it has a nice round number for K. We don't have to use this. We just go ahead and use the value of K and the value of T for this formula right here. So we're going to go ahead and do that. So we have 750 for T. And we have 6.0 for K. So 6.0 for K equals A, E, and I'm going to actually, let me go ahead. I want to write it down lower because I want to write that exponent kind of big so you can see it clearly, not try to crowd it onto a line. So I'm going to go down here. So it's 6.0, I'm right here, equals A, E, okay, and that's going to be to the minus 136,000 joules. We got to convert to joules. Why? Because R is in joules. And it's joules per mole, actually. Over R, which is 8.314 joules per mole Kelvin. And then that's times, I'll put a dot for the times, the temperature. Again, we're using the pure temperature, not 1 over temperature. So in this case, for this combination, this particular point on the graph, it's 750 Kelvin. All right, so let's see units cancel. Kelvin cancels with Kelvin. Moles up here cancels with moles down here, and joules here cancels with joules there, so we have no more dimensions left there. And the rate constant is going to be, for this, it's a second order equation. We get that from the table. It's going to be 1 over molar, 1 over seconds. Let's not worry about that too much. Let's just compute the numbers though, and we'll get to the units at the end. Okay, so we have 6.0 equals A times this whole thing. So you're going to take, you want to be careful with the math and using the calculator. Feel more comfortable, just go ahead and compute this number first, write it down, and then go in and say E raised to whatever that number happens to be. Why don't we go ahead and do it that way? You don't want to try to do too many things on a calculator during a big test. There's too much chance of making a mistake. So keep the calculations as simple as possible. Let's just compute this first. So it's negative 136,000 divided by 8.314 divided by 750. And that's going to give us negative 21.81. Okay, so now what we have then is we have E A to the E to the negative 21.81. All right, so let's go ahead and do this now. Second ln gives us e to the power negative 21.81, and that gives us, this whole thing gives us A times 3.373 equals 6. Divide both sides by 3.373. And what you get is, I'm sorry, that's to the negative 10. I missed that. So let me correct that. Okay, so now we're going to divide both sides by this. And this goes away. What you end up with is A equals 1.779. I'm going to stop there, times 10 to the 10th. Anytime you got a number that big, you can always be a little bit suspicious that maybe something wasn't quite right. But in fact, that is the correct number, and the answer that the book would show is A equals, because of significant figures, they just call it 1 times 10 to the 10th power. All the units had canceled out above, so that is in fact your final answer. I'm always a little worrisome when I got a number that big. That's 10 billion, and but that is in fact the correct answer for this problem.